Hello. In this lesson, we will continue to discuss integrals. However, now we focus on definite integrals, which represent the area under the graph of f in the segment AB, where an area under the x-axis is considered negative. Our building blocks for this area are rectangles, and we are calculating the actual area as a limit of the total area of a collection of rectangles. We first divide the interval to n small segments, on top of which we create n rectangles, each with height equal to the supremum of f in that relevant small segment. The area of that collection of rectangles for each n is bigger than the actual area that we want to calculate. But as n tends to infinity, we get a better upper bound. If the limit exists, we call that upper bound the upper Darboux sum, or the upper Darboux integral. We repeat the procedure, only this time we pick the infimum for each small segment and get an estimation for the actual area from below. This limit, if exists, is called the lower Darboux sum, or the lower Darboux integral. Like in every good sandwich, if those two bounds agree on L, the actual area we wish to calculate is also L. Whenever this is the case, we say that f is Riemann integrable on the segment AB, and the integral is L. When both the supremum and the infimum is on our side, we can repeat the procedure and pick, for every small segment, any choice between those two, and the limit is guaranteed to converge to L. This is called the Riemann sum. Sufficient condition for all those sums to converge to the same limit is that f is bounded on AB and piecewise continuous. That is, we can divide the interval to finitely many small segments such that f is continuous on each small segment. In the case that the antiderivative exists, the fundamental theorem of the calculus let us get the area under the graph by the following formula, meaning that all we have done in the previous lesson can be used here. Integrability and having an antiderivative is not exactly the same. However, we can use all the integration techniques for any integrable function and calculate the area using the formula above, although technically capital F may not be differentiable everywhere on the interval AB. For almost all the questions in the subject math exam, this subtle distinction is not important. Questions concerning the definition of the Riemann sum are easy to spot and easy to solve once spotted. Whenever you see a limit of a sum with two indices, most likely this is the Riemann sum and the sum is an easy integral. What we need to do is to make the summand look like an area of a rectangle with base 1 over n, and the height dependent on the position of the small segment enumerated by k. Take a moment to observe this. In this case, we get that the height is 1 over the rightmost point of each small segment. So the sum represents the integral of 1 over x on the interval 1, 2. And the answer follows. I won't be dwelling on this example since the GRE will most probably have at most one question like this. So, thanks to the Riemann sum, all the toolbox from the last lesson is applicable here. Also, note the following basic formulae, which should be familiar. It is important to understand that we can change the values of f on a finite set of points in the interval without changing the value of the integral. This is not true for infinite set. For example, take the constant 0 function and change it to 1 over the rationals. We get the Dirichlet function, which is not Riemann integrable. For a continuous f, we can conclude this version of the mean value theorem. Observe the following graph and calculate the area of the gray region. First, note that such area can be obtained by subtracting the area under the lower function from the area under the upper function. However, the lower function is best described by 1 over x on the interval 1, 2 and x squared over 8 on the interval 2, 4. So basically, we are calculating two integrals in order to find the answer. We can also integrate with respect to y, meaning look at the curves as a function of y and subtract the area left to the left curve from the area left to the right curve. Here as well, dividing the interval is required. Make sure you understand both integrals and get the same answer in both approaches. Another example. The area between an ellipse and a circle. We can do so by figuring out the curves as function of x, which might not be easy to solve. Another option is to use polar coordinates and treat each curve as a function of the angle theta. First, we need to figure out what would be the interval for theta for each curve. Since both curves are only in the first quadrant, both intervals for theta is from 0 to pi over 2. Recall from the basic module how to visualize the radius rotates as theta grows. The second step is to use the formula for x and y to deduce for each curve the radius as a function of theta. In the circle, it is easy. R is constant. For the ellipse, we need to plug in, isolate r squared, and simplify the formula. Now we need to subtract the r functions and integrate r as a function of theta for each. Right? Wrong. In polar coordinates, the area is calculated by integrating on 1/2 r squared. In the multivariable calculus module, we will see why is that by using the Jacobian, but for now just remember to integrate on 1/2 r squared. The circle part is easy. The ellipse part requires some machinery. So, in order to solve that integral, we first need to get rid of the 2 times theta. Then, we need to spot that this is a rational function of cosine and use the suggested substitution from the last lesson. In this case, this is the formula for dx. And for cosine, for which we need to use the triangle method from the basic module. This method gives us a nice formula for cosine arctangent t. Now, plug all in. The pi endpoint is mapped to infinity, which makes this integral improper. Don't worry about that for now. We will discuss that in details in the next lesson. In the meantime, our integrand is transformed to the form of a rational function of t. And we know that we can solve any integral like that. Note that we simply plug in infinity in order to get the answer. And the final answer is pi over 4, since we need to subtract the two areas. Option 2 was important in order to demonstrate several aspects of integral calculation. However, the easiest way to solve this is by using the well-known area formulae for circles and ellipses, subtract, and divide by 4. Always try to use known length, area, and volume formulae for different geometric shapes when possible. Sometimes we wish to take the graph of a function and create a 3D solid shape by revolving the graph around a certain axis. Calculating the volume of the solid is similar to calculating the area using the Riemann sum, but instead of summing up rectangles, we are summing up disks of radius f of x, and its volume is pi f squared. So the total volume can be calculated using this integral. In case the axis of revolution is the y-axis, we need to consider the contour as a function of y first, and then apply integration with respect to y. Read the following example. These are the curves that will define the contour. We need to deduce the curve's equations as a function of y. Notice the endpoints and calculate this integral, which is subtracting the volume of the solid generated by the inner curve from the volume of the solid generated by the outer curve. Without dwelling into details, if we want to calculate the length of the curve of the graph, we can use this integral. Look at the following example. The calculation is straightforward and the integrand is taken according to the formula above. A related formula is for the surface area of revolution. For example, calculate the surface area of a half of a sphere and observe that we are getting 1/2 of the known formula for the surface area of a full sphere. The next video is a quiz on this material.